Hey, welcome to this video, which is the first in a series that's designed to give you the necessary skills to solve real-world problems. So this series is going to focus on inverse theory, and although I will give you the mathematical background that you need to solve the problems and understand the limitations when we get to it, I'd like to focus on applying that knowledge to real-world problems. So I'm going to be more learning through doing rather than just reiterating mathematics to you. So although this series pertains to inverse theory, we're actually going to take a slight detour over into machine learning from an inverse theory perspective. So we'll start off with inverse theory and then we'll see how we can compose some machine learning problems as inverse problems and then move further on into machine learning from there. Some of the data that we'll see, some of the real world data will also be pre-processed, and some of the techniques that you will need to pre-process that data will be covered in a sister course to this on digital series and image analysis. Now, to do this, we're going to have some programming language, some technology stack. So we're going to use Python, and we're going to lean heavily on NumPy and SciPy packages within there. And when we divert over to machine learning, then we'll also use TensorFlow and Azure Cognitive Services as well, which is a great package from Microsoft. Now, I've covered a lot of technical terms there, but what do they mean? So I think now what I'd like to do is to, first of all, ask for you to subscribe and click like, of course, but also go over what some of these technical terms mean and how they may interact.
So we're going to start off with three circles. And the first circle is going to represent model. Now the model is not something that you typically measure. It is some attributes that we can use further on, and when we explain both the second and third circles, then it might become a bit clearer how the workflow works and what a model is. And we'll give some examples as well. So the second circle here we're going to use to define the maths or the physics of the problem that we are interested in. Again, I'll give examples later and it will all become much clearer once all three are in place and we can then see how they interact. So our third and final circle is going to represent measurements. This is something that you or some system or someone else has physically measured with an instrument. So this can be anything from your height to the radiation coming off the sun. So what happens when we know the model? We know the maths and the physics of the problem, but we have no measurements. Well, we can put that model into that maths and physics, and then we can come out with some theoretical measurements of what might have occurred if we had some receivers. So this is called forward modeling. As an example of forward modeling, here we've had a finite difference approximation of the acoustic wave equation to simulate what that seismic energy would look like as it travels through a model of the subsurface that you can see in the background. So this can be, each frame can be our recordings, our observables, our measurements. So what happens now when we know the model, but instead of the maths and the physics, we actually know the measurements? So we don't know the maths and the physics. Well, this is a classic case of machine learning, when we have some labeled data, so we have models and measurements, and we don't really know the maths and the physics that led to go between one and the other, but we can estimate it with deep neural networks. So an example of this is detecting humans in an image. So previous to this, your labeled data would include a whole bunch of images, which are the measurements, and a whole bunch of labels, so to say that there is a human in this image, or there isn't, or that even could be a bounding box or a mask of where the humans are. And then we don't really know how to go from that image of people to saying that there's a person there, or where that person is in this case, as you see the bounding boxes. But we can use deep neural networks to try and approximate that maths and that physics that we don't quite understand or is too difficult to replicate. So, as you may have guessed, the final option that we have is when we have no idea what the model is, but we have an approximation or a good understanding of the maths and physics of the problem, and we've measured something. So to get from the maths and physics and the measurements to the model, we generally call inversion. And this is a standard setup that we would see in a lot of scientific fields where we make some measurement and we have some good approximation of the physics, and we just want to understand what was the model which led to those measurements that we see. So an example of this might be trying to find the epicenter of an earthquake. So some earthquake happens, the wave travels out, and it's recorded at different times at different recording stations. So we can see these spikes occurring at different times on these seismograms. So the measurements here would actually be the times of the spikes. The physics that we try to approximate is the acoustic wave equation, and the observables, the model, is the epicenter of that earthquake.
Hopefully you've enjoyed this introductory video and I've whetted your appetite for further learning. The next video in the series will cover polynomial regression and we'll also introduce regularisation as well. So thank you for watching, like and subscribe, and I'll see you in the next video.